For the obstacle challenge, our robot Triple Y needs to complete 3 full laps around the field,
autonomously detecting and navigating the traffic blocks to determine the driving direction, navigating corners, and finally making a parking maneuver.
Allow us to walk you through exactly how we navigate through this challenge.
Unlike the open challenge, the robot cannot simply follow walls. Every lap requires a combination of computer vision, sensor fusion, and memory-based decision-making. The run begins inside a parallel parking zone. Before the robot can even start navigating the field, it first needs to move this confined area safely and consistently. This process is handled through a function we developed called exit parking. It moves like an actual automobile. Its movements are based mostly on the front and rear distance sensor together with the steering angles. At first glance, exiting a parking space might seem like a simple movement problem. However, during testing, we discovered that even small heading errors introduced at the beginning of the run could accumulate over multiple laps and eventually affect obstacle avoidance. Because of this, the robot does not rely on timed movements. Instead, every action is guided using real-time sensor feedback. Throughout the sequence, the IMU continuously tracks the robot's heading while ultrasonic sensors monitor the distance between the robot and the nearby walls. The robot performs a combination of forward movements, reverse corrections, and steering adjustments. Once the sequence is complete, the steering is recentered, the heading reference is reset, and the robot prepares for the main navigation phase.
As the robot moves forward, ultrasonic sensors continuously monitor both sides of the course. The robot searches for the first significant opening in the wall surrounding the track. Whichever side produces the larger opening is identified as the navigable path. With the course direction established, the robot enters what we consider the most important phase of the challenge: traffic block detection. For this task, we utilize an OpenMV Cam H7 Plus mounted at the front of the robot. The camera continuously captures image frames and analyzes them using predefined color thresholds that allow it to distinguish between red and green traffic blocks. When a green traffic block is detected, the robot immediately generates an audible confirmation beep and selects a left side avoidance maneuver, with a specified distance, making sure not to hit any blocks because if they were, the robot could stumble upon them for the following runs. However, when a red traffic block is detected, the robot generates another confirmation beep and executes a completely different avoidance routine. Each maneuver was individually tuned and tested to ensure reliable obstacle clearance while minimizing accumulated positioning errors.
We also implemented a fault-tolerant fallback system. If the camera fails to detect any valid traffic block due to camera disconnection, the robot could automatically default to the red path. At first, this seems unusual, but this behavior was intentionally designed to simplify troubleshooting. Without a fallback system, the camera failures could cause unpredictable robot behavior.
On the course, the robot contains dedicated navigation routines for every possible arrangement. For example, if the first detected obstacle is red and the second obstacle is also red, the robot executes a completely different movement sequence than it would for a red-green or green-red combination.
Every section of the course, the robot stores the detected traffic block colors, the avoidance function selected, and the movement sequence that successfully completed the maneuver. This information is saved into a custom memory structure that we refer to as our lap recording system.
Once the first lap is complete, the robot walls and transitions into what we call replay mode. This is one of the most significant optimizations implemented in our design. Computer vision is one of the most computationally expensive operations performed by the robot. Every image frame must be captured, filtered, analyzed, and classified before a navigation decision can be made. While this process is necessary during the first lap, repeating it during every lap would waste valuable competition time.
By this point, the robot already knows which function should be used, what blocks are encountered, and how the movement sequence should be executed. Because of this, the camera processing detection is skipped entirely for the remaining 2 laps.
The robot then executes its final parking maneuver using the same combination of ultrasonic sensing sensing and IMU-based heading control that guided it throughout the whole challenge.
Computer vision, ultrasonic sensing, and IMU-based navigation, adaptive obstacle avoidance, and memory-based path relay, our robot is able to complete the obstacle challenge autonomously and efficiently.